Yes, sir, please start. So please start.
Shall I start?
Yes, sir. Yes, sir.
Okay, okay. Ma'am, your voice is not that much audible. Okay, so I am starting. Okay. So good afternoon, everyone. The topic which is given to me is the carbon sequestration in agriculture soils, current trend and emerging issues. You see, when we talk about the carbon sequestration, basically there are two objectives. One is the soil health improvement. At the same time, we want to mitigate the adverse effect of climate change. So in order to get the benefit of these two things, what we wish to have more and more carbon sequestered in the soils. Okay. So what basically carbon sequestration is? You see, carbon dioxide is present in the atmosphere in the form of carbon dioxide. Sequestration is basically literal meaning is to capture. So what we are doing, we are capturing the carbon dioxide which is present in the atmosphere in the form of carbon dioxide as a photosynthate into the plant. And finally, that photosynthate which we captured through photosynthesis, we want to store that carbon into the soil system. So basically carbon sequestration, and when we talk about the soil carbon sequestration, it is basically the capturing of carbon dioxide from the atmosphere and permanently storing the carbon into the soil system. So the purpose of soil carbon sequestration is to mitigate the climate change mitigation option, and second is to soil quality improvement. When we say soil quality improvement, basically when we increase the soil carbon content, we are improving the soil physical condition, chemical properties, as well as the biological activities. You see, there is no as such why carbon is very important in the soil. Soil carbon itself is not a nutritional element, but carbon is very much important in terms of availability of nitrogen. You see, around 95 to 98% of your nitrogen is coming through mineralization of soil organic matter. And the same is the case with the phosphorus also. Around 50 to 80% of phosphorus is coming through your mineralization of soil organic matter. And same is the case with the sulfur. So apart from this, nitrogen, phosphorus, and sulfur, most of the micronutrients are also we are getting in the soil system through our decomposition of soil organic matter. So soil organic matter is very much important for for improvement in soil health. At the same time, we are decreasing the concentration of carbon dioxide into the atmosphere, from the atmosphere. When we say carbon sequestration, there are three major pathways. One is the oceanic carbon sequestration, another is the geological carbon sequestration, and third is the terrestrial or biological carbon sequestration. As a soil scientist, we are concerned with the terrestrial or biological carbon sequestration. When we say biological carbon sequestration, there are two parts. One is the soil carbon sequestration, another is the forest carbon sequestration. So today we will be dealing about the soil carbon sequestration. So we are coming to the terrestrial carbon sequestration. You see, ocean is the maximum storing carbon dioxide from the atmosphere. Next to ocean is the soil, which 75% of carbon pool is on the land. So primarily soil is storing carbon in the form of organic matter. You see, when we talk about the concentration of carbon dioxide in the atmosphere, it is around 610 petagram. And if we compute the total amount of carbon which is present in the above ground biomass, it is around 700 petagram. If you combine these two, so the amount of carbon which is present in the atmosphere and the amount of carbon which is already present in the form of plant biomass, it is coming around 1300 petagram. Whereas 1 meter of soil depth, it contains around 1500 petagram of carbon. That means soil has got a tremendous capacity to store carbon. And when we consider 2 meter of soil depth, it contains around 2500 petagram of carbon. So soil has got a tremendous capacity to store carbon. Now, why we are talking so much about the soil carbon or soil carbon sequestration? You see, industrial revolution took place around in the year 1750. So around 250 years ago, the amount of carbon dioxide concentration in the atmosphere was 280 ppm. And in the year 2020-21, we have around 412 ppm of carbon dioxide in the atmosphere. So over a period of around 250 years, there was hardly increase of 150 ppm of carbon dioxide in the atmosphere. So it's not a very big issue. But the problem is that in the last 2 decades, now the carbon dioxide concentration in the atmosphere is increasing at an alarming rate. Now it is increasing at a rate of around 0.4% every year. That means every year around 1.6 to 2 ppm of carbon dioxide concentration in the atmosphere is increasing. So in the next 50 years, what will be happening? What will be happening? Around 100 ppm of more carbon dioxide will come into the atmosphere. So the total carbon dioxide concentration in the atmosphere will be more than 500 ppm. So this is the main problem. Now carbon dioxide concentration in the atmosphere is increasing at an alarming rate. When we talk about the methane, the trend is almost similar. There is 148% increase in the methane emission if we compare with the industrial revolution, and same is the case with the nitrous oxide emission. When we talk about the chlorofluorocarbon, only this chemical concentration in the atmosphere is decreasing. The reason is that now we are not using chlorofluorocarbon in our refrigeration work. Apart from that, carbon dioxide, methane, and nitrous oxide, all these three gas are increasing at an alarming rate. So when we talk about the who are the major emitters of carbon dioxide, no doubt USA and China are the two most emitters of carbon dioxide. But apart from that, Japan, Russia, and India is also a fifth largest emitter of carbon dioxide into the atmosphere. Although our per capita emission of carbon dioxide is very low, but when we say the total emission of carbon dioxide, India comes fifth in the world. So India is a major contributor of this greenhouse gas emitter. Now, these are some of the global initiative on climate change. Some of you must be very much aware about the IPCC, where Intergovernmental Panel on Climate Change, then UNFCCC, Kyoto Protocol, and then REDD. Among all these, Kyoto Protocol was very important. You see, the Kyoto Protocol was signed in the year 1997 in Kyoto in Japan. So at that time, it was made mandatory for all the industrialized nations to reduce their fossil fuel emission 5% below the 1990 level. So whatever the industrialized nations they were emitting in the year 1990, they have to reduce their emission by 5% below in the year 1997. But what happens? Instead of decreasing the emission of this carbon dioxide into the atmosphere, all the industrialized nations, they were emitting more of the carbon dioxide. So the treaty was modified, and this Kyoto Protocol was modified in the year 2001 in Germany, and two more clauses were added. First, the clause was added that countries are allowed to subtract from their industrial carbon emission certain increase in carbon sequestered in sinks such as forest and soil. It means that if you are emitting around 100 unit of carbon dioxide, and if you are sequestering around 20 or 30 unit of carbon dioxide into the soil system or into the plant system, then you can subtract that emission from your total emission. That means you are only emitting 70 ppm of or 70 unit of carbon dioxide. And the second thing is that countries are allowed to trade emission allowances that can reduce the abatement cost. Suppose if I am developing a technology, and by using that technology, if some country is reducing their carbon footprint, then I can subtract that amount from my total emission. So these two important clauses were added in Kyoto Protocol in 2001 in Germany. So now coming to the global carbon budget, you see the major emitter of carbon dioxide is from the fossil fuel emission and from the cement production. It is coming around 7.2 gigaton of carbon. That means plus sign is indicating that this much amount of carbon dioxide we are emitting into the atmosphere. But when we talk about the net ocean to atmospheric flux, ocean is basically it is sequestering the carbon. It is sequestering around, it is capturing carbon around 2.2 gigaton of carbon every year. And the same is the case with the net land. Net land to atmospheric flux is also negative. That means land is also sequestering around 0.9 gigaton of carbon every year. So overall balance, if you see, we are emitting around 4.1 gigaton of carbon every year into the atmosphere. So 4.1 gigaton of carbon we are emitting every year. Now, a very important this conference of parties 21 COP in 21, one more concept was added, which is known as 4 per thousand concept or 4 per mil concept. According to this concept, India was also one of the signatories of this COP21, and it was said that if we will be able to increase our carbon stock by 0.4% every year in a to a depth of 40 centimeter, then we can easily offset this around 4 gigaton of carbon dioxide, what we have been emitting. So if we can increase our carbon stock by 0.4% every year to the depth of 40%, we can offset the total emission of carbon from fossil fuel as well as from cement industries production. So this is one of the very important initiative, and India was also one of the signatories of this COP21. So from where this 4 per thousand or this 4 per mil concept came, you see the total emission is around 8.9 gigaton of carbon. Yeah, so we are emitting around 8.9 gigaton of carbon through our fossil fuel burning and through our this industrial emissions. But when we talk about the 2 meter of soil depth, it contains around 2,400 gigaton of carbon. So if you divide this 8.9 gigaton of carbon by 2,400, it is coming around 4 per thousand, that is around 0.4%. So if we will be able to increase our carbon stock annually by 0.4%, we can all easily offset the emission of around 8.9 gigaton of carbon. So what are the options and what are the biophysical barriers to this soil carbon storage? The first barrier in soil carbon sequestration is the water. You know, for any biomass production, we need to have a water. So there is a definite relationship between the above ground biomass and the below ground biomass. If your biomass production will be less, the below ground biomass production will also be less. So there will be less of carbon sequestration. The second limitation is your nutrient. You see, soil organic matter has a definite ratio of carbon is to nitrogen is to sulfur is to phosphorus. So if there is a imbalanced nutrient and there is a limitation of nutrients, then there will be not much of soil organic matter stabilization. So this is another barrier. And the third barrier is the conversion of this organic biomass for fossil fuel burning or for other purposes. Hello. सर मैं ये कर रहा हूँ क्लास ले रहा हूँ. Okay. And the fourth is the soil. We know soil has got a limited capacity. So this particularly the land degradation and erosion, this is also creating another barrier. So what are the options by which we can increase the soil carbon content? So the most obvious answer is the conservation agriculture. In conservation agriculture, we are basically following the three principles. One is the minimum disturbance of soil. Second is the residue retention. And third is the crop diversification or crop rotation. And the second best option is the go for the agroforestry measure. There will be more of carbon input. More will be the carbon input, more will be the carbon stabilizer to the soil system. And third is the recycling of organic residues. We have to convert our organic residues into farmyard manures or the compost, and application of these will definitely increase the soil carbon content. We also have to preserve we have to restore our degraded land. We have to curtail the erosion. And also we need to have some support in innovations with appropriate government policies. And we have to also stop the crop residue burning. Now coming to the mechanism of soil carbon sequestration, how carbon is getting sequestered into the soil. What is the mechanism behind it? Basically, there are three mechanisms. One is the physical protection, another is the chemical stabilization, and third is the biochemical stabilization. You see, when we talk about the biochemical stabilization, it is nothing, it is the inherent constituent of the soil organic constituents. You see, soil residues, these residues are made up of polyphenol, tannin, waxes. If your residues contains higher amount of polyphenol, tannin, waxes, it will not be very palatable to the microbes. So the decomposition will be very, very slower. Once the decomposition will be slower, there will be more of chance of carbon stabilization. Second mechanism is the chemical stabilization. You see, our clay particles are mostly negatively charged. At the same time, our organic matter, they also have a carboxylic or the phenolic groups. So they are also negatively charged. So the polyvalent cations like aluminum, iron, calcium, they act as a bridge between the clay particle and the soil organic matter. So from one side, they are attached with the clay particle. On the another side, they are attached with the soil organic matter. So the microbes, or it cannot easily be detached from the soil particles. So this is the another mechanism by which carbon is getting stabilized in the soil system. And the third and the most important mechanism is the physical protection. In physical protection, what happens? The organic matter is encapsulated from all sides by your clay particles. So it leads to the formation of micro aggregates. So, so there will be, then once the organic matter is trapped inside the clay particles, it will not be accessible to the microbes. So microbes cannot reach to the substrate. So there will be the less of decomposition. So by this way, physical protection is one of the most important mechanisms of soil carbon stabilization. The same is depicted through this figure. You see, biochemical resistance is nothing. It is since the residues, they are very high in, say for example, Prosopis juliflora or Acacia nilotica, they contains higher amount of polyphenols, tannin, waxes. So these compounds are not very palatable to the microbes. So microbes, they don't like it. So they will not decompose it. Once the decomposition will be slower, the chances of carbon stabilization will be much higher. Coming to the chemical stabilization, you see here iron and calcium, they act as a bridge between the negatively charged organic matter and the negatively charged soil particles, clay particles. So by means of ligand exchange, they are holding the organic matter very tightly. So microbes cannot easily detach this form of soil organic matter. And the third, which we discussed already, is the physical protection. Here is the soil organic matter. It is encapsulated by clay particles from all sides. So it becomes inaccessible to the microbes. So microbes cannot reach to this substrate. So they cannot decompose the soil organic matter. Once the decomposition will be slower, the chances of carbon stabilization will be very, very higher. Now, coming to the some newer concept, one of this concept is the soil carbon saturation limit. Earlier, what it was thought that you go on adding the soil carbon, you go on adding the carbon input to the soil system, the carbon content of the soil will indefinitely or linearly increase. But this is not the fact. Each soil has got its upper limit beyond which you cannot increase your soil carbon content. That upper limit is known as soil carbon saturation limit. Then the question comes, when the carbon content of the soil will increase? The carbon content of soil will only increase if your input is more than the respiration. When we say respiration, there are three components of respiration. One is the microbial respiration. Microbes are respiring. They are also emitting carbon dioxide into the atmosphere. Second is the decomposition of soil organic matter. Okay, organic matter after decomposition, they are also releasing carbon dioxide into the atmosphere. And the third is the fine roots which are present in the soil. Their plant roots are also respiring. So if your carbon input by means of residue, by means of biochar, by means of FYM, by means of compost, if your carbon input certain period of time, it will again go back to a certain steady state, which is also called a quasi-equilibrium state. Once the soil will reach the quasi-equilibrium state, it will remain in that state over a very long period of time until unless again some new management intervention is proposed. Suppose at this quasi-equilibrium state, again you are putting some more amount of carbon input, then again the carbon content of the soil will increase. But after some period of time, again another quasi-equilibrium or steady state will reach. So a time will come, even if you go on adding the carbon input, the soil carbon content will not increase. That upper limit is known as soil carbon saturation limit. So you can you can understand this soil carbon saturation by these two figures. You see, one condition is that if you assume there is no saturation. So if you apply 5 ton, 10 ton, 20 ton or 40 ton of FIM, what will happen? The carbon content of soil will linearly increase. So if you apply 5 ton, one steady state, 10 ton, another 20 ton, another steady state, and 40 ton, another steady state. If there is no saturation, then what will happen? If you plot it linearly, the carbon content of the soil is linearly increased. But this is not the fact. The fact is that soil has got its saturation level. So beyond which you cannot increase the soil carbon content. So you go on and adding 5 ton, 10 ton, 20 ton, but this will not cross this saturation level. This is the upper limit by which you can increase the soil carbon content. Then coming to what is the implication of soil carbon saturation limit? Suppose if you have a limited quantity or meager quantity of organic resources, and if you have got two soils, one soil is having a higher saturation. This is the saturation limit, and this is your soil carbon, actual carbon content. So this is your saturation deficit. So higher the saturation deficit, greater is the chance of soil carbon stabilization. So soil A is nearer to saturation. So if you have limited quantity of soil organic matter, you must apply this organic matter to soil B, because here the chance of carbon stabilization will be much higher. So how to compute this soil carbon saturation? In your whole lifespan, you cannot compute this soil carbon saturation by doing some experiment. So what is the option? The option is the use of the crop cycle simulation model. And some of the authors like Hassink and Six, they have already proposed, if you know the silt and clay content of your soil, you can find out your soil carbon saturation level. So you have to multiply your silt and clay content with 0.29, and this is the intercept. You add this intercept. This is basically a straight line equation, y is equal to mx plus c, where m is the slope. So you have to multiply 0.29 into silt plus clay content plus 6.9. You will get your soil carbon saturation limit. You see the average unit is here is gram carbon per kg. And if you are using the this is the equation of Hassing. And if you are using the equation of 6 at all, you have to multiply it by 0.21, and your intercept will be 14.76. Either you are using this Hassing equation or 6 et al equation. Both will come to a almost similar level. So you can determine the soil protective capacity if you know the silt and clay content of the soil. So what will be the saturation deficit? Saturation deficit will be 1 minus what is the soil organic carbon content divided by protective capacity of your soil. So likewise, minimum threshold of soil carbon can also be determined. Also, we can determine the soil carbon saturation limit. Now, coming to what is the impact of cultivation on soil organic carbon content. Since we are talking about the agriculture soils, so we have been doing this cultivation over a very long period of time. A very good classical work was done by Jenny and Rai Chaudhary. You see, they did this work in the year 1960. At that time, they collected samples from different agroecological regions of the country. And they, at that time, transported those samples to USA in Berkeley. In UC Davis laboratory, they determined the total carbon content. And what they told that Indian soils have depleted around 30 to around 60% of their native soil carbon content. So this is the opportunity we have depleted around 30 to 60% of our initial total carbon content. So this is, in other words, is the opportunity before us that we can increase our soil carbon content by 30 to 60%. Okay. So these are the various means by which we can increase our soil carbon content. One of the important measure is the use of conservation agriculture, biochar, agroforestry, desert control, afforestation, pasture management, water harvesting, then farming system approach. By adoption of these practices, we can easily increase the soil carbon content. These are some of the work what we have done, I have done. So we have calibrated the global carbon model, Rothamsted carbon model, which is one of the most important model to know if you are going to change your management intervention, what will be its impact on your soil carbon content. So we have validated this ROSC model by utilizing the data set of long-term fertilizer experiments of India. We collected the soil samples from Jabalpur, Palampur, and Louisiana. One is the vertisol, another is the alfidol, and the third is the inseptizol. So it is covering almost all the three major soil orders, and we have validated or parameterized the model, calibrated the Rossi model for the Indian condition. So by using this model, what we observed that by using this Rossi model, we can, the observed and predicted values are very nearly matching. So we can use it for the simulation purpose. Suppose if you are going to apply certain management practice that from next year onward, you will be applying around 5 ton or 10 tons of FIM. What will be the soil carbon content after the lapse of 20 years or 30 years or 40 years? So by using these models, you can easily find out the impact of your management intervention on your soil carbon content. So we have predicted the model up to 2070. We can see that in the case of NPK plus FIM, there is a very huge, the soil carbon stock is increasing very steadily. In case of NPK, where we are following the balanced application, it is almost constant. And in the case of control, there is a slight decrease in the soil carbon content. The same similar is the case with the Palampur or Ludhiana. But you can see that in case of Jabalpur, where the soil contains greater amount of clay, the chances of carbon stabilization is very, very higher. So the amount of carbon stock will be much, much higher in case of Jabalpur as compared to Palampur or alfizol or inseptizol. This is the percentage change under the different carbon pools. You see, in case of Jabalpur, if we are switching from NPK to NPK plus FIM, majority of carbon is going towards the active pool. As a researcher, we want to know if we are adopting some good agriculture management practice and if there will be some change in the soil carbon content, in which pool it is contributing. So we found in the case of Jabalpur, majority is carbon is going towards the active pool. Whereas in case of Palampur alfizol, majority of carbon is going towards the resistant pool. Whereas in case of alfizol of Ranchi, here carbon is majority, it is going towards the active pool and the resistant pool. So these are the practices by which we can increase the soil carbon content. One is, you see how the carbon content, I told you earlier already that your input should be more than the respiration. So either there are two ways by which you can increase the soil carbon content. Either your input should increase, or else the decomposition of soil organic matter should be reduced. So, or else if you are following the both the practices, increase the carbon input, decrease the decomposition, then the chances of carbon storage will be much, much higher. So how to attain these things? So how to increase the soil carbon input? Go for the rehabilitation of the degraded land, or switch from agricultural land use to agroforestry land use or the forest land use system. Second thing, what you can do is the go for the reduced tillage. Once we are going for the reduced tillage, what will happen? Lesser volume of soil will be exposed to the atmosphere. So the oxidation of carbon will be much lesser. Once the oxidation will be lesser, there will be less chance of carbon is escaping from soil to the atmosphere. So going for the no-till system, going for the reduced tillage will definitely increase your soil carbon content. Another is the improving the cropping system. Go for the introduction of legumes or the cover crops in your cropping system. There will be increase in the soil carbon content. If we will be able to increase our nitrogen use efficiency, also by improving the nitrogen use efficiency, we can increase the soil carbon content. Here I would like to tell you that if you are reducing your nitrogen rate also, basically you are reducing your carbon footprint. Why I am saying this? Even production of 1 kg of nitrogen is generally emitting around 2.2 kg of carbon dioxide into the atmosphere. So if you are reducing your nitrogen dose by 20 kg, that means around 40 to 45 kg you are sequestering. Okay, so by increasing the nitrogen use efficiency, also you can increase your soil carbon content. Residue management is the another very important aspect. So if you go for the conservation agriculture, where we are retaining our residues of the previous crop, instead of going for the incorporation, go for the retention of the residue, this will definitely increase your soil carbon content. And if you are applying some amount of organic input like FIM or compost, then the soil carbon content will definitely increase. And second important thing is the use of the biochar. Why biochar is important? Because if you the same amount of biomass, if you will put into the soil system, what will happen after the lapse of 2 to 3 years? Around 90 to 95% of the soil carbon, which plant carbon, which is present in the biomass, will again decompose and it will again go back to the atmosphere. But once you are converting your biomass into biochar, immediately you are losing 50% of your biomass carbon, but remaining 50% of your biomass will have a very recalcitrant carbon. So that carbon will remain as such for next 100 or thousands of years in the soil system, because biochar carbon is very recalcitrant in nature. So microbes cannot decompose that carbon. So conversion of biomass to biochar is a very good means of sequestration of your atmospheric carbon dioxide. Then there are some future strategies like we have to go for the deployment of perennial green crops. We instead of going for that, we have to go for the future crop breeding priorities. Also, we have to breed our annual crops for having a deeper and the larger root system. You see, there is a definite relationship between the above ground biomass and the below ground biomass. So if your above ground biomass is around 100 tons, that means around 25 tons is the below ground biomass. This is the thumb rule. So 25% of the total biomass is your below ground biomass. Higher will be the input of below ground biomass, there will be greater chances of your soil carbon sequestration. So conservation agriculture is a very good option by which we can increase our soil carbon content, mostly in the upper layer of the soil. At the same time, it will help you in the improvement of your soil quality. It improves your water infiltration, water stable aggregate. Nitrogen mineralization is fairly higher under the practice of conservation agriculture. Enzymatic activities are much better as compared to the conventional agriculture. And definitely there is a stratification of phosphorus and potassium in the topsoil layer. Also, we will be reducing the methane oxidation and there will be reduction in the carbon dioxide and nitric oxide emissions. So conservation agriculture is one of the very good means by which we can mitigate the climate change, adverse effect of climate change. At the same time, we can improve the soil quality also. So the option is go for the reduced tillage instead of going for the conventional system. If you are not going for the no-till system, at least we must reduce our tillage operations. If we are going for 3 or 4 tillage operations, then try to go for the 1 or 2 tillage operations. You will be less exposing your soil to the atmosphere, so there will be less chance of oxidation of your carbon. If you are going for the no-till system, definitely the soil carbon content in the top layer of the soil will increase. So long-term no-till promotes associate stratification between the topsoil and the subsoil. At the same time, no-till reduces biological soil organic carbon oxidation, decrease soil temperature, increase water holding capacity, improve water infiltration, and slows the turnover of macro aggregate and prevent erosion also. So then second is the one is the you go for the reduction in your tillage operation. Second management intervention you can go for the residue management. In case of residue, go maintenance, it is very essential for the maintenance of soil organic matter. At the same time, it is preventing your wind and water erosion. At the same time, it acts as a mulch, so your availability of water in the soil will also increase. It will moderate your soil temperature. It will improve your nutrient reserve because it's a good source of potassium. At the same time, it contains good amount of nitrogen and phosphorus also. You see your residue contains around 0.4 to 0.5% of nitrogen, around 1 to 1.5 or 2% potassium, and around 0.2 to 0.25% your phosphorus. So it's a good mean of your nutrient also. So if you are retaining your residues in the soil system, that means you are conserving your nutrients also, nitrogen, phosphorus, and potassium also. It improves your soil nutrient reserve, promote healthy soil biological communities. It provides wildlife habitat and increase crop performance also. Now coming to how to decrease the decomposition. You see, increasing soil organic carbon stocks can be achieved through increasing carbon sequestration or through reducing decomposition rate of soil organic matter. So if you are going for the no-till system, then definitely you are exposing less volume of your soil to the atmosphere, so there will be less chance of oxidation. And if you are storing more and more carbon into the below ground biomass in the form of root biomass, so definitely the decomposition will be much slower in below ground biomass as compared to the above ground biomass. So again, coming to, if you are going for the conservation agriculture practices, there will be improvement in soil structure. So your soil water retention will improve by 5 to 15%. There will be much improvement in case of mean weight diameter. Regarding greenhouse gas emission, definitely there will be reduction in 5 to 10% of carbon dioxide. It is generally said that nitrogen mineralization is fairly high under the practice of conservation agriculture. So there will be improvement in 20 to 40% of nitrogen mineralization. There will be phosphorus and potassium stratification in the top layers. And also there will be good fungal diversity. You can see from this figure, this is the arbuscular mycorrhiza. Wherever we are following this conservation agriculture practice, there was 46% higher AM as compared to the conventional system where we are not retaining any residue. So your microbial population will definitely improve. Microbial biomass content will also improve. Now coming to, what are the qualitative judgment by which we can say that this soil has got a good carbon sequestration potential? So if you know the temperature and the moisture rainfall of your region, you can easily say that in which region your soil falls for in terms of soil carbon sequestration. You see, if your temperature is less and the rainfall is high, most of the temperate, say for example, Himachal Pradesh, where the temperature, mean annual temperature is fairly less, but at the same time, mean annual rainfall is more than 2000 millimeter. So there the carbon sequestration potential is very high. If your mean annual temperature is less, but your rainfall is also less, that will fall under the category of medium. If you have got a very high temperature, but at the same time you have got a very good amount of rainfall, then you have got a medium in terms of soil carbon sequestration potential. If you have a very high temperature, mean annual temperature is very high, at the same time rainfall is very low, that means you are coming under the category of low carbon sequestration potential. Some of the western part of our country which falls under the category of, even Punjab, Haryana, parts of Rajasthan, Gujarat, they are coming under this category low. But majority of soils of India, they are coming under the low to medium category. Now, you may be thinking, if I will be practicing this particular good agriculture practices, what will be the soil carbon sequestration rate? This is the meta-analysis done by Fujisaki et al. What they found that if you go for the organic inputs, like if you're applying FIM and compost, then there is a chance of 0.45 megaton. That means 450 kg of carbon you can sequester every per hectare per year. If you are going for the balanced fertilization and mineral, going for the wherever it is, we are going for the balanced fertilization, there you can expect around 240 kg of carbon per hectare per year as a soil carbon sequestration rate. If we combine, if you are going for the integrated nutrient management practices, it will be coming around 340 kg per hectare per year. If you are following the crop rotation or reduced tillage plus input, there is a tremendous amount of soil organic carbon changes. And the duration of these studies varies from 7 to 22 years. Dr. Ratan Lal also, Smith et al., they also compute can be achieved. They told that if you go for the crop rotation with perennial crops, go for the agroforestry system, then there is a chance of around 0.88 ton of carbon dioxide you can sequester per hectare per year. If you are going for the no tillage, minimal tillage, agroforestry measure, land cover change, cropland to native vegetation into the soil system, entire amount of biomass after 4 to 5 years, hardly 10 to 20% of carbon will be retained. But if you are going for the biomass to biochar production, 50% of carbon you are immediately losing, but remaining 40 to 50% of carbon will be permanently sequestered by the biochar. So if you are applying organic residue to soil, what will happen after the lapse of 5 years? Around 10% of carbon will remain in the soil system. But if you are going for the biochar making, you are capturing around 50% of biomass carbon as such, and it will remain as such for next hundred or thousands of years. What is the need of biochar in India? One is we know we have a very serious issue of crop residue burning. Our soils are inherently low in soil carbon content. We know every year carbon dioxide is increasing at an alarming rate, and also there is the environmental degradation. But when we convert our biomass into biochar, there are so many competing use of these organic residues. One thing is that people may go for the soil incorporation. It can be used for animal fodder. It can be used for bedding purposes. It can be surface retained, as in the case of conservation agriculture, or else we can go for the compost making. So these are the competing uses other than this biochar making. So if you have biomass other than these processes, then you go for the biochar make, and the carbon which will be sequestering, which will be very permanent in nature. So if you talk about the what is the potential of biochar in India, so this is the total amount of this much amount of million tons of crop residue we are producing every year. Around 500 to 600 million tons of crop residues is produced every year. Out of this 500 to 600 million tons of crop residues, around 234.5 million tons is the surplus residue. So can we think of converting this surplus residue to biochar? So this is one of the options by which we can make the biochar. And if you analyze the nutrient element in the rice and wheat residue, you can think of if you are getting 7 tons of if you are going for 7 tons of rice residue, it contains around 42 kg of nitrogen, 7 kg of phosphorus, and 105 kg of potassium. And in case of wheat residue, it is around 25 kg of nitrogen, 4 kg of phosphorus, and 50 kg of potassium. So if you are going for the burning, that means if under the rice wheat cropping system, we are losing around 82 kg of nitrogen, around 40 to 44 kg of phosphorus, potassium, at the same time sulfur, calcium, magnesium, and definitely carbon also. So what are the impact of biochar application in agriculture? So there will be improvement in soil structure. Definitely soil water retention capacity will be increased. So biochar is another use of biochar is that biochar is a very good material for liming of acid soil. So it's a very good substitute of liming material because the biochar pH is very high. So it acts as a liming material. And so we can easily apply this material under the acid soil condition where the response to crop will be fairly high. So if you apply biochar, there will be definitely improvement in aggregate stability. There will be decrease in the GHG emission. Soil nutrient dynamics, definitely it is going to change because biochar is a very porous in material. It has got a honeycomb-like structure. So it will be retaining nutrient in its various porous structures, and that will be subsequently available to the plant. So fungal diversity is increased with the application of biochar, and definitely it's provide a niche for the microbial population. These are some of the meta-analysis done with the biochar study. So their majority of people are saying that with the application of biochar, there is a tremendous increase in the soil pH. And wherever the pH is less, there is a more increase in the soil pH. When we talk about the types of the different feedstock has got a very good response in terms of, so if your feedstock is leguminous in nature, then the impact on crop production is fairly high. Then the temperature, if we are going for the slow pyrolysis, and if you are going for the high pyrolysis, generally at low pyrolysis biochar, it gives a better response to the crop yield. Finally, I am coming to the conclusion slide. So we have to devise a time-bound strategy for improving our carbon storage in agriculture soil. So we have to take into account of what is the existing soil carbon content and what is the soil texture and climate of the region. Depending upon that, we can think of up to what level of soil carbon content we can increase. Second thing is that we need to define the what is the attainable soil carbon deficit. We need to map the soil carbon map of the country. What is the actual carbon content? Up to what level we can achieve? So what is the gap? So in order to fill the gap, we need to identify the best management intervention like balanced fertilization, INM practice, conservation agriculture, or else residue incorporation, crop rotation, or biochar application. And the third thing what we can do that, since time we cannot conduct an experiment for a period of 30 and 40 or 50 years, so well calibrated models like Rossi or Century should be used to know the exact time frame for attaining the desired result. So these are some of the way forward. Efforts should be made to offset the process of land degradation. We have to change our land use pattern. We have to shift from agriculture to agroforestry or agri-silviculture. There is a need to explore new method to accelerate market development for carbon farming. Now we are talking of carbon credit in agriculture. Already initiatives has been taken by different ministries. So definitely in coming years, people will be rewarded if they will increase the soil carbon content. So what we need to have a policy and procedure that should be framed for the auditable and verifiable account of the baseline condition and whatever the additional benefit from adopting the best management practices. There is an urgent need for standardized, low-cost, adaptable approach for soil organic carbon accounting. This is all these things are related to carbon credit market. Also, we need to develop a efficient greenhouse gas policy so that can provide incentive to farmers according to the global warming potential on account for the total mixture of emission and sequestration factors. So what I will conclude that government should formulate a policy for farmers to provide incentive in form of subsidy or insurance for adoption of well-defined good agriculture practices for soil carbon sequestration. So I can say that the future of agriculture is conservation agriculture. We have to make effort so that our gains should be more than the losses. So this is all about my presentation. Thank you very much for your patient hearing. If you have any specific question, we have around 8 minutes of time. We can discuss all those things. Thank you.
Thank you, sir. Thank you very much, sir, for a very enlightening and engaging talk on carbon sequestration, throwing some light on conservation agriculture and also on agroforestry aspects. And also, I could see few slides related to biochar, what is its impact on soil. Sir, I am very sorry I could not introduce you in the inaugural in of your beginning of your lecture, sir. I was on a
No issue,
field
no
visit.
issue.
There was no internet connectivity, sir. I have just came a little at a lower altitude. I urge all the participants to have interaction with our respected speaker. Sir has a very good experience on carbon sequestration and stabilization under the practices of conservation agriculture. Sir has a vast experience in this field. He was also a visiting scholar at the Ohio State University, Columbus, USA. So I urge all the participants to have, if any questions or queries they have, they can directly ask our speaker or they can put their queries in the chat box. We have the number and email ID of Jasser. I will be sharing that in the WhatsApp group. If anybody is having some clarifications, please raise your hand or you can directly interact with our speaker. Yes, any questions? Sir, if you are able to access the chat box, I don't think there are any. Someone has raised hand. Ramakrishna, please go ahead. You can unmute and interact with our speaker.
Please unmute.
Ramakrishna ji, please unmute yourself. Hamida madam, are you there? Jannat ma'am.
Sir, just give me a second.
Our one of our participants is not able to unmute. Please,
Let
if you can help him.
yeah, sure.
Ramakrishna, if you are able to unmute, please go ahead with your question. Madam, please see whether he will be able to. He is still saying that he is unable to.
So I'm checking the same.
Sir, in the meantime, sir, we have a question in the chat box.
Mm-hmm.
From Parul Sharga that in agroforestry systems, up to what depth we should collect soil samples for estimating soil carbon sequestration?
I think you see, for agroforestry system, at least we should go for the 1 meter depth. For
Okay,
agricultural crops, it is generally advisable up to the depth of 30 to 45 centimeter, but preferably up to 30 centimeter, because you see in agriculture crops, most of the fine roots, 80% of your fine roots is concentrated in top 20 centimeter of your soil depth. So generally for agriculture crops, it is said you go up to the depth of 30 centimeter. For agroforestry, at least you should go for the 1 meter depth.
Thank you, sir.
Sir, very good afternoon.
Very
Good
good.
afternoon, Rama.
Sir, I am Ramakrishna, very informative and